Welcome to this ninth lecture on calculus of variations. This is the ninth lecture in the series. So, what we are going to do is we are trying to derive this Euler's famous Euler's equation for obtaining the extremas of functionals. Okay, this is also called Euler Lagrange equation. Okay, Euler Lagrange equation. So we want to derive this Euler's Lagrange equation for obtaining the extremas of the functional, and for that we are only 4 lemmas away, and after that we are ready with all the ingredients required for deriving this Euler Lagrange equation. So let us try to understand what these lemmas are. Actually, there are these lemma 1, 2, 3, and 4. We are going to use this lemma 4 for deriving our Euler's equation, and for deriving this lemma 4 we need this lemma 2. We are proving this lemma 1 and 3 because actually these lemmas are symmetric, only this they are all like their proof is similar, and this lemma 3 we will need further when we will move ahead in our course. Lemma 1 we are just making a background to prove this lemma 2. So basically we need these only these 2 and 4 right now. 4 is the lemma we directly use to solve to derive Euler's equation, and lemma 2 we will use to derive lemma 4. Lemma 1 and 3 will need, like lemma 3 will need further, and this lemma is just a like background setting for deriving this lemma 2. So let us start with lemma 1. They are very simple lemmas. Let me just change the color. Okay, let us make it black. Okay, so what we have, our first lemma. First lemma is, it says that if you have this integral a to b alpha x hx is equal to 0, dx is equal to 0, this integral is equal to 0 for every alpha x which is continuous. Okay, you have this, no, I'm sorry, you have a fixed alpha x which is continuous in the interval ab, and then you have this integral is equal to 0 for every hx which is in CAB. What is CAB? CAB is a set of all continuous function in the closed interval AB. This hx satisfies two conditions. One is that it is in CAB, that is, it is continuous in the closed interval AB, and the second is that it is 0 at the boundaries. It is 0 at A and B. Okay. If this thing is alpha x is fixed, alpha x is a fixed continuous function in the interval AB, and then you are saying that this integral is equal to 0 for every continuous hx which is such that h of a is equal to h of b is equal to 0, then we claim that this alpha x is actually 0. Alpha x has to be 0 for all x in the interval AB. Okay. So let us prove it. It is very simple. By contradiction, as usual we'll go by contradiction. So let us suppose that this, we want to prove this, that alpha x is equal to 0 for all x in AB. So suppose there is some point in this interval AB where your function is not 0. So let us possible alpha x is non-zero, and if it is non-zero it can be positive or negative. So let us assume that it is positive. You can also assume that it is negative, right? So right now we are assuming that it is positive. So what I am saying is, suppose, start with contradiction. You suppose that alpha x is not equal to 0 at some point in this interval AB, okay? And if it is not 0 at that point, it will be positive or negative. I am assuming that it is positive, and let us call that point is x naught. So we are assuming that let, if possible, alpha x is non-zero, say positive, at some point in AB, and we are calling that point as x naught, right? So I am saying that this is my interval AB. There is this point x naught. I am saying that my function alpha x is positive at this point x naught. Now because alpha x is continuous, okay, alpha x is continuous, it means that it cannot happen like this, that at x naught function is positive and then suddenly it is 0 in this neighborhood of x naught. So there exists a small neighborhood around x naught, okay, in which the function will stay positive, because that is a requirement for continuity. You can say like this: alpha x is continuous at x naught. It means that limit x tends to x naught, alpha of x is equal to alpha of x naught, right? So it means that there exists, for a given epsilon, there exists a delta such that alpha x minus alpha of x naught modulus This is the definition of continuity. Just a minute. Is less than epsilon for all x lying between x naught plus delta, x naught minus delta. Okay, so it means that alpha of x lies between alpha of x naught plus epsilon, alpha of x naught minus epsilon for this interval, right? And now you choose your epsilon such that this is positive and this is positive. Okay, you can always your epsilon can be as small as you want, so you can choose your epsilon such that this quantity is positive, then of course this is positive, right? So you found an interval in which your function is positive. So this is because of continuity. So if alpha x is continuous and is positive at x naught, then there certainly exists an interval around x naught in which your function alpha x is positive. So it means that there exists a neighborhood of x naught in which alpha x is not equal to 0, in fact positive, because at x naught it is positive, we are assuming, and that neighborhood will be some interval, and I am calling that interval as x1 x2. Okay, so I am assuming that there exists an interval x1 x2, open interval, in which alpha x is not 0 and in fact positive. Okay, okay, now now we have to this thing is true, this integral is equal to 0 for all hx which are continuous and satisfy these boundary conditions. So I am constructing a particular hx which is continuous and which is 0 at the boundaries. So see, now we had this point, we assuming the condition that alpha x is non-zero at x naught, we have obtained this x1 and x2. So I am defining my function hx like hx is a function which is non-zero here in this interval x1 to x2 and 0 everywhere else. Okay, I am defining a function hx in the interval ab. How I am defining? I am defining hx is equal to x minus x1 into x2 minus x for all x belongs to x1 x2 here and here, and it is 0 here, it is 0 here. Okay, now you can see that if x when x is lying between x1 and x2, see this thing is positive because this x is greater than x1, and this is also positive because this x is less than x2. So hx is positive in the interval x1 to x2 and 0 otherwise. Okay, and also you can see that hx is continuous. We have to check the continuity only at the point x1 and x2. At x1 the value of the function is 0. At x1 you'll put x1 here, this is 0, and at x2 this is again 0 because of this term. So you had 0 here, 0 here, like this you have your function. So your function hx is continuous in the interval ab, and also h of a, because h of a is 0 and h of b is 0, because the function is like this, function is 0 here, 0 here, then like 0 here, up to here it is 0, then in this region this is this. Okay, this is a second order curve, quadratic curve. Okay, so it means that the hx so chosen is such that it satisfies all the conditions of the lemma. Okay, so now we have alpha x positive in the interval x1 x2, and we have hx which satisfy all the conditions of the lemma, and hx is positive in the interval x1 x2. Now because this hx is satisfying all the conditions of the lemma, so this integral has to be 0, because that is what our lemma says for this particular hx. Okay, so let's see, let's move to next slide. Okay, so for that particular hx, now we had see this integral. Okay, this integral a to b alpha x hx dx. Now these functions are non-zero only from x1 to x2, so this will change from x1 to x2 alpha x, we don't know what it is, but we know that it is positive, and hx takes this value x minus x1 x2 minus x dx. Now this is positive in x1 x2 and this is positive in x1 x2, therefore this integral has to be positive. The final integral has to be greater than 0, but lemma says it has to be 0. Okay, therefore we reach at a contradiction. Therefore whatever we have assumed is wrong. Therefore our assumption is wrong. What was our assumption? Our assumption was that alpha x is non-zero at some point in the interval AB. It means that alpha x is equal to 0 for all x in AB. Hence, proved. This is what we need to prove. We wanted to prove. So we have proved that if alpha x is continuous and alpha x hx dx is equal to 0 for all hx which are continuous and 0 at the boundary, then alpha x has to be 0. Okay, now let's move to next lemma. Lemma 2. Lemma 2 is similar. It again starts with you have a fixed alpha x which is continuous in the interval AB. Okay, and you have this integral 0. You have an integral which is alpha x times h dash x dx is equal to 0 for all. This is first derivative of hx. So here now in the last lemma hx was continuous, but here we are using the derivative of hx, so we need that derivative exists. So hx is in d1ab. D1ab is the space of functions where first derivatives of the functions are continuous in the closed interval ab. So we have this thing. This lemma is true for all hx which are in this space d1ab and which are such that h of a is equal to h of b is equal to 0. Okay, if this is true that this integral is equal to 0 for all hx which are in the space d1ab and which satisfy these boundary conditions, then alpha x has to be a constant. Okay, then alpha x has to be a constant. So let us prove it. Okay, we want to prove that alpha x is equal to a constant, and this constant we will choose in our lemma. When we want to prove it, we'll wisely choose this constant c. Okay, so I'll just tell you how this c is chosen, but we can have this intuition for c when we prove. We'll go further, we'll see why we choose this c, this particular c like this. So I'll just define like this for like starting. Let c be a constant, and this is how I'm defining my c. Okay, I'm defining a constant c such that integral a to b alpha x minus c dx is equal to 0. Okay, this is how our c is chosen. Okay, now we need in the last lemma we have seen that we have constructed a hx which was continuous and 0 at the boundaries. Now we need to construct an hx which is in the space d1ab. It means that it has continuous first order derivative and which satisfy these boundary conditions. So let us construct one such hx. So I am constructing that hx like this. Okay, hx is integral alpha zeta minus c d zeta a to x. Okay, this is a dummy variable. You can put t also, anything you can put. The integral is not from a to b but a to x. So this will be a function of x. Okay, so now if we can simply this is very easy to see that this function is differentiable. Okay, you can prove that this function is defined like this is a differentiable function. Then then we can easily prove that hx is differentiable, and indeed it has a continuous derivative. Okay, you can find what the derivative is. Let us find what the derivative is. How we can find the derivative of the hx? We can use the Leibniz rule for differentiation under integral sign. What is that? Leibniz rule is this. It says that if you want to differentiate, you have an integral ax to bx fxz dz. You want to differentiate this. So what is the rule says? It says that this differentiation is equal to ax to bx derivative of the integrand, that is partial derivative with respect to x, plus derivative of this upper limit db by dx times the function integrand calculated at this bx minus differentiation of this lower limit dA by dx times the function, the integrand evaluated at that lower point. So this is what the Leibniz rule say. Now we want to differentiate this thing with respect to x. So first you this term, the first term, you differentiate the integrand with respect to x. There is no term containing x, so that is 0. Okay, this term is 0. Now second is you differentiate the upper limit, that is dx by dx, that is 1. Okay, dx by dx is 1 times the integrand calculated at this point. So in place of zeta you'll put x, alpha x minus c, that is this second term. Now third term is you have to differentiate the lower limit with respect to x. This is a constant, so lower limit is 0. So only this term will contribute. So you get that alpha h dash x is equal to alpha x minus c. Okay, right? So I have constructed a function hx which is such that in the space d1ab, which is in the space d1ab, and its derivative is alpha x minus c. You have computed the derivative by Leibniz rule. Now you have to see whether these conditions are satisfied, because for lemma, for this integral, lemma says that integral is equal to 0 for all hx which are in the space d1ab plus the boundary conditions, these boundary conditions. So let us see whether h of a and h of b are 0. You can easily see that h of a is integral a to a. Integral a to a will be 0. And h of b is a to b alpha zeta minus c d zeta. Is that thing 0? Yeah, that is 0 because that is how we have chosen our constant. Okay. Now you can see why I chose my constant like that. Okay. That is written in next slide. Let's see. So this, the h of a is integral a to a, that is 0. Okay. H of b is a to b alpha zeta minus c d zeta is equal to, this is equal to 0. Why? Because this is how we have chosen our c. Okay. So from here we got that intuition that we have to choose our c like that. Okay. Therefore now our hx is such that the hx which I have constructed is such that it satisfies all the conditions of the lemma, right? Therefore this integral will be 0. Okay. This integral will be 0. Okay. So no, I'm sorry. Constructed by the lemma, therefore we have this alpha x h dash x dx is equal to 0, a to b. This is by lemma. Okay, this is by lemma, right? Now consider this thing, a to b alpha x minus c h dash x dx. What is this? This is equal to a to b alpha x h dash x dx. Just I multiply like this, minus c times integration of h dash x will be hx, and then computed at b minus computed at a, c times h of b minus h of a. Now this thing is equal to 0 by the lemma from here. Okay, this thing is equal to 0 using the lemma, and this thing is equal to 0 because h of b is equal to 0 and h of a is equal to 0, right? So we got that this integral is actually 0, right? Now there is another way to compute this integral. Again start with the same integral. Okay, you have computed the value of h dash x. What was the value of h dash x? We have computed in the last slide. This is alpha of x minus c. So this thing is actually a to b alpha x minus c whole square dx, right? So because these are like they are same integral, in the first approach you have seen that this integral is actually 0. So you are saying that this integral is equal to 0, but this is positive. Okay, this can be 0. The integral of a positive quantity from a to b can be 0 only if that quantity is 0. Okay, so it means that alpha of x minus c is equal to 0 for all x in ab. It means that alpha of x is equal to c for all x in ab. Okay, hence proved. This is the lemma we will use to prove lemma 4, and then lemma 4 we will use in our when we derive that Euler's equation. Okay, so we can skip actually lemma 3, but for the sake of completeness we can derive that also. It's not very hard, it's like similar proof. Let's go to lemma 3 now. I'm sorry. Okay, lemma 3 says that if you have similarly a continuous function in the closed interval ab, and you have this integral a to b alpha of x h double dash x is equal to 0 for all hx which are in the space d2 ab. What is this space? This is a space of all functions which have second order continuous derivatives in the closed interval ab, and which satisfies the boundary condition h of a h of b is equal to 0, h dash a h dash b is equal to 0. Okay, so this lemma says that if hx is chosen like this, satisfying all these conditions, I'm sorry, if hx is chosen like this, okay, then then your alpha x is equal to c naught plus c1 x. Okay, c naught plus c1 x for all x in AB, where c naught and c1 are constants. This is the lemma. Okay, we can prove this lemma. This is like a very technical proof. Like there was like lots of intuitions are involved in actually proving this lemma, but we can just go technically and see how this lemma is proved. So you can see that there are two constants involved. So you have to choose these constants wisely, and for choosing two constants you need two equations. So let your C naught and C1 are defined by these conditions. First condition is this, okay, that your alpha x minus C naught minus C1 x dx from A to B is 0. Second condition is that your alpha zeta minus C naught minus C1 zeta d zeta from A to x. You compute this will be a function of x, then integrate it from A to B with respect to x, that should be 0. These are the two conditions. For computing C naught and C1. Okay, right? And now you need to have Hx which is in space G2AB and which satisfies these four conditions. So this is that Hx. This is how I am choosing my Hx. Hx is equal to A to zeta At minus C naught minus C1 t dt. This will be a function of zeta. Then I can integrate this with respect to zeta. And from A to x, not from A to b. So it is easy to prove that this function hx is in the space is in D2AB. It means that you have to prove that this is twice differentiable function, and in fact the second order derivative is continuous. That we can prove using the simple calculus. Okay. Okay. So it means what I am saying that it can be easily shown that hx has second order continuous derivative and boundary conditions also. You can just simply put a, you can see that h of a, h of b is equal to 0, h dash a, h dash b is equal to 0, right? For example, your uh, hx was a2 x d zeta a2 zeta at minus c naught minus c1 t dt, right? So you can see h of a will be a to a, that will be 0. H of b is equal to a to b, that will be 0 because that is how we have chosen our c1 c2. Similarly h dash a you can compute by Leibniz rule, and then you can see that that is also 0, and similarly h dash b you can compute by Leibniz rule, and you can see that that is also 0 by the choice of a and b, c naught and c1. Okay. So it means that this particular hx satisfies all the conditions of the lemma. Okay, so it means that a to b alpha of x h double dash x dx is equal to 0. Okay, now we need to compute these derivatives also. You had this h of x is equal to a to x z zeta a to zeta at minus c naught minus c1 t dt. So what will be h dash x using Leibniz rule? What you will do? First you have to differentiate the first term is, I'm sorry. First thing is you have to differentiate this integrand with respect to x, but there is no term containing x partial derivative. Therefore, that first term in the Leibniz rule is 0. Second is you differentiate the upper thing with respect to x, that will be dx by dt, that is 1, dx by dx, that is 1, times the integrand computed at, I'm sorry. This is the integrand computed at x. So you have to put zeta, instead of zeta you have to put x. Okay, this is your first derivative. Now you will compute the second and the third term also 0 in the Leibniz rule. The second derivative, again we have already computed this derivative, right? So it will be ax minus c naught minus c1 t. Just a minute. Okay. I'm sorry, what is this happening? Just a minute. I have messed up the things. Okay, now it's fine. Okay, so these are the derivatives we have computed. Now see this thing. Concentrate on this integral. This is integral a to b alpha x minus c naught minus c1 x h double dash x. What is this? This integral has three terms, one with this, one with this, and one with this. So I am separating that terms. The first is as such a to b alpha x h double dash x dx. This is 0 because of this lemma condition. Okay. And the second is c naught times h double dash x, that will be c naught times integral of h double dash x will be h dash x computed at b and minus a. So that will be c naught times h dash b minus h dash a. This is equal to 0 because we know that h dash b is equal to 0 and h dash is equal to a is equal to 0. Minus c1 times x times h double dash x dx. Okay, so this is 0, this is 0. So we are left only with this. Now what is this? c1, integrate this by parts. When you integrate this by parts, what you will get? You will get first function x times derivative of second function, that is h dash x a to b, minus differentiation of first function, that is 1, integration of second function, that is h dash x dx a to b. So when you will finally compute this thing, this will be b times h dash b minus a times h dash a, that will be integration of h dash x will be h of x, that will be h of b minus h of a. Now we know that this is equal to 0, this is equal to 0, this is equal to 0. All the terms are separately 0, so this is equal to 0. So you get that this integral is actually 0. Okay. Now there is a second way to integrate this. We have computed our h double dash x. What was that? That is ax minus c naught minus c1t. So this integral is actually alpha x minus c naught minus c1x square dx, right? And because these are similar integrals, so in the first approach that you have seen that this integral is equal to 0, therefore this is equal to 0. Now you are saying that integral of a positive quantity is 0 from a to b. That is possible only when that quantity is equal to 0. Therefore you get that alpha x minus c naught minus c1x square is equal to 0 for all x in ab, and square you can remove, so you get alpha x minus c1 minus c1x is equal to 0 for all x in AB. So you get that alpha x is equal to c0 minus c1 plus c1x, where c0 and c1 are constants for all x in AB. Okay. So this is how we have proved our lemma 3. Now let's move to lemma 4, which we will directly use in derivation of the Euler equation. So this is the lemma for what it says as, it says that if you have two continuous functions alpha x and beta x which are continuous in the interval closed interval ab, and if this integral a to b alpha x hx plus beta x h dash x is equal to 0, dx is equal to 0 for every hx which is in the space d1 ab. Okay, this space is space of all functions which have first order continuous derivatives, and where this hx satisfies these boundary condition. If this happens, then this beta x is actually differentiable and its derivative is equal to alpha x. Okay, so lemma says that if you have two continuous function alpha x and beta x, only continuity is required. Okay, then and your hx is in the space d1 ab which satisfies these boundary conditions such that this integral is equal to 0 for all such hx, then your beta x is actually differentiable and its derivative is equal to this function alpha x. Let us prove it. You start with this part only, this integral, first part. Okay, a to b alpha x hx dx, integrate it by parts. When you integrate it by parts, okay, what you'll get, first function hx into integration of second function, that will be a to x alpha zeta d zeta from a to b, minus differentiation of first function, that is h dash x, integration of second function, that is a to x a zeta d zeta dx. Okay. Now what is this? This is, we will put b minus a. H of b is 0 and h of a is equal to 0, right? Therefore you have this thing, this quantity is equal to 0. First quantity is 0. And what is this? You assume that this is a of x. You assume that this quantity is a of x. Then this is equal to minus a to b a of x h dash x dx, right? So now you can write your integral, like it means that this term can be replaced with minus a to b ax h dash x dx. Therefore your star can be rewritten as The first term you are replacing with minus ax h dash x plus beta x h dash x. You can take the h dash x common, so you get minus ax bx beta x, right? For all hx which are in the space D1AB and satisfying this h of a and h of b is equal to 0. Now you can see that these are the conditions of lemma 2. These were the conditions required in lemma 2, right? These were the conditions of lemma 2, and that is the integral of lemma 2. So what lemma 2 will say? Lemma 2 will say that this integral is actually constant. This integrand is actually constant. So what you are saying, that a function which is continuous times, you can see that your alpha ax is this. You can easily prove that this is continuous. In fact, this is differentiable. You can easily prove the differentiability of this function ax. So you have this beta x already continuous, this function is continuous. You have a continuous function times h dash x dx is equal to 0 from integration is from a to b for all hx which are in the space d1ab and satisfying these boundary conditions. So this is nothing but lemma 2. So lemma 2 will say that this integral is equal, this integrand is equal to constant. Okay. So by lemma 2, you get that this integrand is equal to constant. Okay. So it means that beta x is equal to ax plus a constant. Okay. And this ax is this a to x alpha x d zeta. And this is differentiable. We can prove that. So differentiable function plus a constant. So it means that beta x is differentiable. And you can derive this. The derivation will be using Leibniz rule. You can differentiate it. This will be dx by dx times the integrand computed at x, that is alpha x, plus differentiation of constant function, that is 0. So we proved that beta dash is equal to alpha x. So this was lemma 4. Okay, this lemma we will use for proving the Euler's equation in next lecture. Okay, we'll prove. Okay, thank you.